We can observe this diagram. At our left we have the input devices: keyboard, mouse, scanner, biometric, microphone, camera. Those are the input devices. Computer accept input through these input devices. It does the processing as per the requirement arises. The data are passed to the memory, and for saving those data permanently the storage devices are used. So again, memory accept the data from the storage devices, and again computer CPU fetch those data from the memory. You can observe the flow of this diagram, and after processing all the data and all the instruction which has been passed out by the input devices, ultimately the data goes to the output devices, and through the output devices like monitor, projector, printer and headphone, we the user, the ultimate user who are using the computer system, visualize or see those data. So let us understand how the CPU work. To understand the working of the CPU, we have to understand the processor. That is, let us discuss about the 8086 processor. We can observe at our right we have the pin diagram of 8086 microprocessor. It is consisting of 40 pins, and those 40 pins are divided into two units. Half of those pins are used by the bus interface unit, and another half of the pins are used by the execution unit. Let us understand that 8086 microprocessor is an enhanced version of 8085 microprocessor that was designed by Intel in 1976. It is a 16-bit microprocessor having 20 address lines and 16 data lines that provides up to 1 MB storage. It consists of powerful instruction set which provides operations like multiplication and division easily. Intel 8086 is a 16-bit HMOS microprocessor. It is available in 40-pin deep chip. It uses a 5-volt DC supply for its operation. The 8086 uses 20-line address bus. It has a 16-line data bus. The 20 lines of the address bus operates in multiplex mode. The 16 low order address bus have been multiplexed with data, and 4 high order address bus lines have been multiplexed with status signal. We can observe the diagram given below. Total 40 pins have been divided into two parts. At our left we have 20 line address bus, and at our left 16 line, that is data bus, and the 20 line address bus that is further divided into two parts: 16 low order address bus and 4 high order address bus. The CPU chip is consisting of different kind of register. So we have to learn what is register. A processor register or CPU register is one of a small set of data holding place that are part of the computer processor. A register may hold an instruction, storage address or any kind of data such as a bit sequence or individual characters. A register is a temporary storage area built into a CPU. Most modern CPU architecture include both type of registers. Internal registers include the instruction register IR, memory buffer register, that is MBR, memory data register, that is MDR, and memory address register, that is MAR. At our right we can observe the diagram of the register, different kind of register. Those are found in 8086 chips. So let us move and start learning about the 8086 chip and the register that is belonging to the 8086 microprocessor chip. Let us understand the internal architecture of 8086. So the 8086 has been divided into two units. One is bus interface unit and the other one is execution unit. So 8086 chip is divided into two functional units. Bus interface unit, it is known as BIU, and execution unit, that is known as EU. Now let us discuss about the bus interface unit. We can observe at our right we have the diagram, and in that diagram we can observe the red color border. So this is the diagram of 8086 microprocessor chip that is separated into two parts. At our right we have the execution unit, and at our right in the red color border I have separated to show you the bus interface unit. So the bus interface unit perform the following four functions. It fetch the instructions or data from the memory. Therefore we have to understand that the bus interface unit is used to fetch the instruction from the memory. The memory is nothing but the RAM. So the CPU fetch data from RAM. So inside the microprocessor chip, the bus interface unit does the particular operation. So it fetch the instructions or the data from the memory. So this particular operation is done by the bus interface unit. So another operation, it read the data from the input port. So bus interface unit also read the data from the input port. Another function, it write the data in the memory. So the processor sends the data in the memory, that is RAM. So inside the processor, inside the microprocessor 8086 chip, the bus interface unit does this operation. So bus interface unit operate this function. It write the data, after processing it write the data in the memory, that means in the RAM. It write the data in the RAM. So another function, that is function number 4, write the data in the output port. So the bus interface unit also write the data in the output port. So these are the following four functions that is operated by the bus interface unit under the 8086 microprocessor chip. So to operate these following four functions, we have the number of functional part. We have to discuss those. So the functional parts of the bus interface unit to perform these four operations are segment register, and the other part is instruction queue. So now we are going to discuss about these two parts. So these are the functional parts of the bus interface unit to perform the above mentioned four following functions. So which are those parts? Segment register, that is one part, and other part is instruction queue. Now let us discuss about the segment register. We can observe at our right we have the diagram of 8086 microprocessor chip, and you can observe I have drawn a red color border to show you the segment register. So it is a register having memory space of 1 MB of 8086 chip that is divided into 5 blocks. of capacity having maximum of 64 kilobyte for each block. The following are the 5 blocks. Code segment, it is known as CS. You can observe in the diagram CS, that is the code segment. Code segment is a 16-bit register containing address of 64 kilobyte segment with processor instructions. The processor use CS, that is code segment, for all access to instructions referred by instructions pointer, that is IP, that is IP register. So another register you have to understand, that is data segment. It is known as DS, followed under the code segment. You can observe data segment DS. It points to the data segment of the memory where the data is stored. So it just point to the data segment. DS used to point the data segment of the memory where the data is actually stored. Another part is stack segment. It is known as SS. It is usually used to store information about the memory segment that is stored the call stack of currently executed program. So it is usually used to store information about the memory segment that store the call stack of currently executed program. Another part is extra segment. It is known as ES. This segment register to gain access to segment when it is difficult or impossible to modify the other segment registers. And the last block is instruction pointer. It is known as IP. It is a 16-bit register that holds address of the memory location of coming instruction to be executed. So the next instruction which will be executed, that particular address of the memory location is that is stored in the 16-bit register known as instruction pointer. So this particular instruction pointer hold the address of the memory location of the particular data that is coming to execute next. So the instruction which is just going to execute next, that particular instruction's memory location address is pointed by this instruction pointer. So these are the 5 registers. These all are the registers categorized under the segment registers. So now let us discuss about the instruction queue. Instruction queue. There are 6 blocks in instruction queue, and BUI, that is bus interface unit, performs its operation in parallel with execution unit as follow. BIU, bus interface unit, fetches the instruction byte while execution unit is executing the operation. The prefetch instruction is saved in a group of high-speed register that is known as instruction queue. We can observe the diagram at our right, that is drawn with red border. So the red border portion is the instruction queue. You can observe this is the part of the bus interface unit. So which are the instructions that is going to be followed next are being maintained in a queue. So the execution unit will access the instruction from the bus interface unit, and it will just execute the instruction according to the priority that is being set into the instruction queue. You can observe the diagram. So you can observe with the arrow it has been drawn the flow of the execution. The ALU will one by one will fetch the instruction according to the priority that is been set up in the instruction queue. So the instruction queue along with the segment register are the two important part of the bus interface unit. Now let us discuss about the execution unit. So we can observe in the diagram the red portion has been highlighted, that is the execution unit inside the part of the 8086 microprocessor chip. So the execution unit perform the functions. It direct the bus interface unit that where to fetch the instruction or data from. After receiving information from the instruction queue of the bus interface unit, it decode the instruction. It execute the instruction. It contains the control circuit to perform various internal operations. So these are the four operations that is performed by the execution unit of the 8086 microprocessor chip. And for operating these four functions, it has some functional register. Let us understand those functional parts. So functional parts of execution unit to perform those four operations: general purpose register, pointer and index register, ALU, flag register, timing and control unit. These are the 5 parts. So let us understand all these 5 parts one by one. Let us understand the general purpose register. General purpose registers are used for temporary storage of data and memory access. Since the processor access register more quickly than memory, 8086 has 4 16-bit general purpose register, that is AX, BX, CX and DX. These are available to the programmer for storing value during programs, and each of those is further divided into two 8-bit registers. So we can observe at our right in the diagram the red color border, that is data register, that falls under the execution unit head. So you can observe there are 4 registers: AX, BX, CX and DX. So these 4 registers togetherly known as data register. So these are the general purpose register. So we can observe, I have drawn a table. So at our left we have AH, that is A higher order, and followed by AL, so that is A lower order. So these two are togetherly known as AX. So AX, that is 16-bit register, and this 16-bit register is further subdivided into 8-bit plus 8-bit, that is A higher order and A lower order. So this is the accumulator, and it is generally used for arithmetic and logic instruction. So we can observe in the next row we have BH, that is B higher order, and BL, that is B lower order, and togetherly known as BX. So this BX is 16-bit register, and that is further divided into two 8-bit register, that is BH, B higher order, and BL, B lower order. This is the base register, and it is used to store the value of the offset. And in the third row we have CH and CL, C higher order and C lower order, togetherly known as CX. So CX, that is also a 16-bit register, further divided into two 8-bit register, that is CH and CL. It is the counter register, and it is used in looping and rotation purpose. And in the last row we have DH, DL, and togetherly known as DX. This is the data register, a 16-bit data register, and it is used in multiplication and input output port addressing. Now we will discuss about the pointer and index register. In the right we can observe the red color border. These are the registers which falls under the pointer and index register pattern. So in this category we have 4 registers. Let us discuss. 8086 microprocessor has 2 pointer and 2 index registers are follow. Pointer, stack pointer known as SP. This stack pointer SP register is used to indicate the location of the last item put into the stack. When you push something into the stack, the SP is decremented before the item is placed on the stack. Another is base pointer BP. Usually base pointer BP is used for preserving space to use local variable, and followed by index register. One is source index. The source index register is generally used to store the offset of source data in data segment. And another is destination index. Destination index register used to store the offset of destination in data or extra segment. These index registers are specially used in string manipulation. Now let us understand what is ALU. It is a 16-bit register that performs arithmetic and logical operation of both 8 bits and 16 bits. The ALU performs simple addition, subtraction, multiplication, division, and logical operations such as OR and AND. An arithmetic unit or ALU enables computer to perform mathematical operation on binary number. They can be found at the heart of every digital computer and are one of the most important parts of a CPU, that is central processing unit. At our right you can observe the diagram. The red color border has been highlighted the portion of the ALU inside the 8086 microprocessor chip. Now let us understand about the flag register. It is one of the most important part of the 8086 microprocessor chip. It is a 16-bit register having 9 usable flag bits and 7 unused flag bits. Usable 9 flags are further divided into following parts. Status flag, it is 6 status flag. Another is control flag, it is 3 control flag. Let us understand all those in detail. We can observe the table given above. Those 6 status flag are as follow. That is carry flag. It is shown by CY. You can observe the table above starting from 0 to 15. So it is 16-bit starting from 0 to 15. Total it occupies 16 bits. So it is a 16-bit register. The flag is a 16-bit register, and there are 9 usable bits, and other you can observe 7 blank bits. So let us understand those 9 bits is further divided into 6 status flag bits and 3 control flag bits. So starting with the carry flag bits, this is carry bit. If some operation are generating carry after the operation, this flag is set to 1. Otherwise this flag is set to 0. So this particular carry flag will let us understand that whether it is holding any carry or not. If the carry flag is set to 1, that means it is holding a carry after operation. If the carry flag is holding 0, that means there is no carry. That is why the flag is set to 0. So followed by auxiliary carry flag. It is in short name known as AC. When some arithmetic operation generate carry after the lower half and send to the upper half, the AC, that is auxiliary carry flag, will be 1. Otherwise it will be 0. Now let us understand zero flag. In short name it is known as Z. If the total register is 0, then only the Z flag is set, otherwise it is not set. Now let us understand the sign flag. In short name it is known as S. After any operation, if the MSB is 1, then it indicates that the number of negative. So if the number is negative, then it will set to 1 and this flag is set to 1. So if it a negative number, then this sign flag will set to 1, otherwise the sign flag will set to 0. So if the sign flag is set to 1, that means it is a negative number, so that carries the sign. So that means if the sign flag is set to 1, that means it is negative number. If the sign flag is set to 0, then that is not the negative number. Now parity flag, that is known as P. This is even parity flag. So it is also known as even parity flag. Why? Because when result has even number of ones, so we know that computer only understand zeros and ones. So if there are even number of 1, so that means all ones, if you count the number of ones, so if the numbers are even, then it will be 1. So this particular parity flag will set to 1, otherwise 0 for odd number of ones. So if the total number of ones is in odd number, then the parity flag will be set to 0, otherwise the parity flag will set to 1. Assume there are 4 ones, that means 4 ones, that means 4 is a even number. If there are 4 ones, that means 4 is a even number, so the parity flag will be set to 1. If there are 3 or 5 or 7 ones, that time the parity flag will be set to 0. Let us understand the overflow flag. The overflow flag is known as O. The overflow flag is set to 1 when the result of the signed operation is too large to fit. So if in any case the result of the sign operation is too large to fit in the memory place, then the overflow flag will be set to 1. Now let us understand another 3 control flag. So these 6 flags are the status flag. So these 6 flags are the status flag. Now we are going to learn about 3 control flag. One is direction flag. This is directional flag. This is used in string related operation, that is d equal to 1. Then the string will be accessed from the higher memory address to the lower memory address, and if the d is equal to 0, then it will do reverse operation. So let us understand the interrupt enable flag. This is interrupt flag. If I equal to 1, then MPU will recognize the instruction from peripheral. For 1 equal to 0, the interrupt will be ignored. So now let us understand the trap flag. This Trap flag is used for on-chip debugging. When t equal to 1, it will work in a single step mode. After each instruction, one internal interrupt is generated. It helps to execute some program instruction by instruction. Timing and control unit. This has not been shown in the diagram properly, but still we have to learn because this is one of the most important functional unit. Timing and control unit, part of the execution unit in the microprocessor 8086 chip. We use timing and controlling unit in 8086 for the generation of timing signal and the signal to control. All the operations and functions, both interior and exterior, of the microprocessor are controlled by this unit. Every operation in the entire 8086 system occurs with the given synchronization process with the clock.